All right, thanks everyone for coming. It's a pleasure to be at AI Ukraine again. It's not my first time on the stage, but for those of you who have met me for the first time today, I work at DataRobot. I work primarily with automated machine learning. So the subject of this talk is pretty dear to me because developing an engine that builds reliable production-ready models and validates them robustly is kind of my full-time job. Other than that, I teach a little bit and compete a little bit when I have when I have time left after the first two. So let's define what the problem of target leakage is and how it can present itself and how we can prevent it. So for those of you who'd like to follow some code examples, I have them, and I have the copy of the presentation available at this GitHub repo. So for those of you who have their own laptops, feel free to download this stuff and follow it on your own machines. But it's not necessary, it's not mandatory. So yeah, do whatever is comfortable for you. So how can we define target leakage? So it can present itself in many different ways, so it's pretty difficult to give a definition that covers all possible cases, but a general attribute of target leakage is when we kind of contaminate our training data with some information that gives away the target, either acts as a correct answer for the target or acts as a proxy that can hint us greatly towards the correct answer for this prediction row. And this usually happens as a result of some mistakes made by the data scientists during various stages of the data science project lifecycle. So the core problem of data leakage is that when we collect our training data set and we train our supervised machine learning models, we get some sort of contamination from the future that sneaks into our data from the past. And why is this a problem? This is a particularly nasty issue because if we have target leakage in our training data, the result of that would be that we will get very good validation score when we develop the model locally, when we test it on our evaluation sets, but we only start seeing the consequences once we deploy the model into production. So this particular issue of target leakage leads to having good validation scores when we develop the model, but once we deploy the model into production, we get unpleasant surprises. So our models start suddenly being very inaccurate, making disastrous predictions, and that can cost money, that can cost clients, that can cost even human lives in the most unfortunate cases. So when I describe this subject, this term of target leakage to some of the data scientists, either at conferences or elsewhere, a pretty common response I got, well, yeah, I've been around the block, I know how to build machine learning models, I know that we shouldn't trust the training score and we should always evaluate our models on out-of-sample data, so I always make sure to do robust k-fold cross-validation, so I should be fine, right? I should be protected against target leakage. Well, not quite. Target leakage can manifest itself in many different ways, and what makes it a particularly tricky data science issue is that it's rarely described in the books, it's rarely described in training materials, but it's something you eventually will discover when you start building real-world machine learning models that solve actual business cases and deal with actual real-world dirty data. And since target leakage can be introduced during any of the stages of the data science project, partitioning alone or validation alone won't save us from all cases of target leakage. So if there's only one thing that I'd like you to carry out from this talk is that target leakage can occur pretty much anywhere in your data science project. So in this talk, I'd like to go through each of the possible stages and explore some examples of mistakes that can be done could be made during each of these data science project stages. And yeah, for the record, every single example that I'm going to show today, I've actually seen data scientists make these kinds of mistakes. So some of the examples might be simplified, but these are examples of actual mistakes I've seen people make. So let's see what bad can happen during data collection. As an easy warm-up exercise, try to spot target leakage in this data set. So for every example, I'm going to assume that we have a tabular data set, so like a relational database or an Excel spreadsheet, and we have a supervised learning problem, so we have a target column we would like to predict. So let's say, what happened to the screen? All right, let's switch to this one. So let's say we have a business case of, so let's say we would like to help people relocate to new job markets. So for example, a Ukrainian data scientist considers a career in the UK, and they would like to know what kind of income they can count on after relocating to the UK. So we can collect some sort of some data set like Glassdoor, some anonymous salary surveys to be able to enter the skills and attributes of this person, and the model would estimate what kind of annual income this person can consider in a new job market. So let's say we have the job title, data scientist, they have some kind of experience, and annual income in USD is in US dollars is our target column. So it's pretty easy to spot that the target leakage in this case is in this column because we have a feature that's kind of a linear function of the target. So we have monthly salary in British pounds. So I actually gave this talk at ODSC Europe in London a couple of weeks ago. So I pulled these numbers from UK job market. And we have a feature that's a linear function of the target. So we already have the correct answer encoded in our feature. So all we have to do is to apply the exchange rate from British pounds to US dollars and multiply it by 12, and we get our target. So it looks simple, but actually in like real life examples, there can be multiple columns that contain different formatting of the same thing, so like different measurement units, inches versus centimeters, or British pounds versus dollars. It's pretty common in real-world noisy data. We can have relational databases or Excel spreadsheets where we have copies of the same features encoded differently. So like different formatting, different text preprocessing, different measurement units, different currencies, and so on, different time periods. So a slightly more complicated example, a pretty common use case in telecom is to predict the demographic group of a subscriber given how they use voice calls, how they use SMS messages, how they use internet data plans. So we have, for each subscriber, we have some information about how many voice calls they make, how many SMS messages they send, how many megabytes of data they use daily. And we would like to predict whether it's a male or it's a female, or predict the age group so that we could target them with better advertising or design some kind of personalized service plans for these subscribers. Maybe create a new service plan, a new pricing model. And what can sometimes happen is once old data get overwritten with new facts. So for example, we have our relational database where we already have the correct answer for each subscriber, and some business analyst wants to create a dashboard or create some kind of a report, so they start creating derived features such as this group column from the target. And it can often happen that we can get another column which is computed after the fact, like from our target column. So like maybe for better presentation purposes or for reporting or for dashboards. And this can also happen. So we can, as a data scientist, we can export a relational table with hundreds of columns, but can easily miss some of the columns, and this column may end up being an aggregate of our target feature. So we actually have the correct answer encoded in this group column. So because we have the first letter M or the first letter F, we can accurately answer whether it's a male or a female because it's future data that's sneaked into the past. So someone mutated our relational data by creating a derived column from the target, and that gives away the target completely. So if we use some kind of text modeling on this data set, our text model will pick up the M character or the F character and will accurately predict the target. So we will have amazing validation scores for our model, but once we deploy it into production, we won't have this derived column in production. And our column will always be empty, and the model performance will suffer once we deploy it. So actually, like all of the examples I'm showing for data collection, they can be summarized as target leakage occurring because our data lacks snapshotability. So a very important thing if you're working with the data that can mutate, where future facts can override previous records, this is a high risk for target leakage. So a slightly more subtle example, let's say we have a typical banking case, credit scoring. So we would like to evaluate, given the purpose of the loan. So the customer is applying for a loan, they have some sort of level of education, they have marital status, they have annual income, they have some description of the purpose, why they want this loan from us. And we would like to predict, like we as a loan officer would like to grant this loan to the customer or reject it. Yeah, that's the target for our predictive model. So we would like to predict whether the customer will default on the loan or not. So can you spot the target leakage here? If we think carefully about our business case, so how we would like to use this model in production. So a customer is not yet our customer, and they walk through our doors and say, I want a loan of $1 million. I have this level of annual income. I'm married. I have 3 kids. I have a PhD. I work full time, so I'm unemployed. Will you give me this loan or not? So we would like to decide right there on the spot whether we should approve this loan or reject this loan before this person is our customer. So once we grant them the loan, they become our customer. So obviously, if the person is not our customer yet, we cannot tell how many times we've already called them to remind them about a late payment on their loan. It's like if we imagine this in a healthcare scenario. So an analogy there would be if we want to predict whether the patient has a disease and use as a feature the number of surgeries our hospital has already performed on the patient for this disease. So this is another example of data from the future sneaking into the past. So this normally happens when our data lacks snapshotability, when we have a database that's constantly overwritten by new facts, new services pumping data into it, and data scientist exports data from the wrong point in time. So data already has contamination from the future, and this will completely give away the target or be a strong proxy for the target. Right, so this is a target leakage. So this is a more subtle example because it highly depends on the actual deployment scenario of this model. So like who will request the predictions from this model and how will they act based on the prediction of the model. So this, like whether the column is target leakage or not, highly depends on the actual deployment scenario of the model and who looks at the predictions and who makes decisions based on the predictions. So what can happen during feature engineering? Turns out that there's a lot of stuff that can happen too that's related to target leakage. So for example, we've been around the block. We've built predictive models for some time. We know that from the mathematical point of view, models like linear regression or k-nearest neighbors are very sensitive to distance metrics or are very, very sensitive to feature scaling. So we would like to pre-process our data set by doing standard scaling in all of our features. So we would like to normalize each of our numeric features such that it has a 0 mean and a unit standard deviation, right? So we know that like scikit-learn, we import our favorite standard scalar class from scikit-learn. We transform the data set to normalize each of the features, then we partition it into training and evaluation folds, so like either doing k-fold or training test split or anything else, and we train our model. So what's tricky in this particular case? The tricky part is that we do scaling before we do partitioning. And this can sometimes lead to a situation where we accidentally leak the information about the distribution of the test feature into our training pipeline. So if you think how a standard scalar works, we need to scan through the entire feature, compute the mean value of this feature. Then we have to compute the standard deviation of the feature, and we have to subtract the mean and normalize by the standard deviation. So, and just because we do standard scaling before partitioning, this means that we learn the mean and we learn the standard deviation on both the training and the test set. So if our test set happens to include some crazy outliers or some very unusual values, this information will sneak into our training pipeline. We will kind of know some information from the test set in our training subset because we use the mean and the standard deviation from the entire data set rather than only the training part. So how to fix this? we fix this by partitioning first and then pre-processing second. So normally how we should approach this situation when we have to infer some pre-processing parameters for a feature, we have to first partition the data into training and validation, and then we do a standard scalar fit, so we learn the mean and the standard deviation from only the training subset, and then we freeze these parameters and use them to transform the evaluation set. So we learn pre-processing parameters on the training subset, and then only transform the validation or holdout or whatever else we'd like to evaluate on. So this can apply to not only to standard scaling, but also to all sorts of features. So we have if we have text columns in our data set, a common mistake I've seen people make, it's quite common for text models to encode them using document term matrices. So like either doing character n-grams or word n-grams and building a giant matrix where the rows are the documents and the columns are the words. So a common mistake I've seen people do is actually learning a vocabulary from the entire data set rather than learning it only from the training set. So the issue there is that language is not static. New terms emerge. New words can appear in our production data that we haven't seen during the training stage. So by learning the DTM on the entire data set rather than only on the training subset, we're creating kind of a perfect world for our model where the model knows all the words that exist in the language and there's nothing that can surprise it. So by doing that, we're eliminating the possibility for our model to deal with out-of-vocabulary words. And the way to fix this would be to make sure that our validation approach actually replicates the problem we will have in production. So we have to only learn the vocabulary on the training subset and and hopefully the test set will include some out-of-vocabulary words where we will be able to evaluate how our model deals with them. So worst case scenario, our model, if we build it in a perfect world like this, it will start raising exceptions in production or behaving in an undefined way. So same deal with categoricals. So for those of you who especially competed on Kaggle, you know that for categorical data, when we have tree-based models, there are some pretty complex and interesting encodings for categorical variables you can do, so like target encoding or credibility estimates or frequency encoding. And the same mistake you can make here is by accidentally peeking into the distribution of the categorical on the test set, so like calculating the frequency of the categorical or mean target of the categorical by using the entire data set rather than only the training part. So the solution here is the same. First partition, then do feature engineering. So what can happen in partitioning? Turns out, even if we partition first and feature engineer second, there's plenty of mistakes we can make in partitioning as well. So one thing, I wasn't expecting to see it here, but I've seen an example of this possibly an example of this in a paper by Andrew Wang's group. So they published a paper a couple of years ago where they claimed good results on detecting pneumonia, edema, emphysema on chest x-rays. So they built a deep learning model that can detect different kinds of diseases from patient chest x-rays. So all looks great. But if we read the actual paper, we see two peculiar things. So they have 1,010 unique images, but only 30,000 unique patients. That means, on average, we can get 4 images of the same patient. And they say they partition the data set randomly into 80% training and 20% validation. So can you see what could go wrong here? Since they partition the data completely randomly, we can get the same patient both in training and in validation. Worst case scenario that can happen, that the model can actually pick up not necessarily the lungs of the patient, but for example, some scarring that the patient had from a previous surgery or a broken bone or maybe some noise introduced by the medical imaging device itself. So it might not necessarily learn the features of the disease, but the features of patient anatomy, because the same patient can cross training and validation. But even if that does not happen, even if the model picks up the disease itself rather than bones or scars or noise from the imaging device, what also happens is if we compute cross-validation score on this kind of partitioning, we actually end up computing a more optimistic cross-validation score than it actually is, because we will effectively be evaluating our model not on out-of-sample predictions, but on in-sample predictions, because we're evaluating the score of our model on the patient we've already seen in training. So we're effectively calculating not out-of-sample CV, but in-sample CV. And they actually fixed it between the two paper versions. So in the third version of the paper, they changed their approach to partitioning the data set. They now say that the patients don't cross training and validation anymore. And actually, many scores have become worse. Some got better, but many of the previously reported scores got worse. That's exactly the issue I was trying to highlight in the very beginning. So the result of target leakage, in this case, target leakage in partitioning, led to us having more optimistic scores than we actually have. So we report better scores than our model will actually have when we deploy it into production. So also an interesting case where I've seen a lot of mistakes made is the so-called cold start problem. So it's common in something like public health or crime models. For example, we would like to predict disease propensity or predict the outbreak of flu or some epidemics. So we have data only on, for example, only on 3 US states, Illinois, Oklahoma, and Texas, and we would like to predict North Carolina. So we deal with a situation when we have only observations from 3 states, and we would like to predict something in a state we don't have in our training set. So we have to learn from 3 states and predict the 4th state. So what we can do here in terms of robust validation is actually make sure that our validation approach represents the problem we're trying to solve with the model. So since our model has to deal with a completely unseen state in production, that means we have to repeat the same framework in our cross-validation. So we have to apply out-of-group group partitioning and out-of-group validation. So if we have to deal with predict an unseen state, that means we have to simulate this situation in our validation framework. So we have to train on Illinois and Oklahoma, predict Texas, then train on Illinois, Texas, predict Oklahoma, train on Oklahoma and Texas, predict Illinois, and like average those scores. So this will be a better representation of how our model deals with an unseen state, so for a cold start problem, than if we had completely random partitioning. So this is something that's useful to keep in mind. So if we have to deal with out-of-group predictions, then we have to apply the same partitioning and validation setup for this problem. So also a common thing that I've seen people, common mistake I've seen people make is oversampling or augmenting data and using the wrong partitioning approach for that. So for example, at Data Robot, we have a limit for the number of rows that the users can upload, and sometimes customers decided, hey, this thing requires me to have n rows in my training data set, but I have fewer than that, so I'll just double every row, like copy every row and upload this like double data set into Data Robot. Or actually, like if we want to do something like oversample the minority target to have a better target class balance, or do some kind of copying of individual rows, we can also make plenty of mistakes there. Also, that can happen with augmentation. So for example, if we have pairwise data, like item A and item B, and we have to predict the similarity of those two items, a pretty obvious augmentation technique is to just like create a mirror image of the data set, and we will have a twice bigger data set for free by doing this kind of augmentation. So there's nothing wrong with oversampling or augmentation here. The part that is wrong is random partitioning. So we will end up with the same situation like Andrew Ng's group had. So we, as a result of random partitioning on oversampled or augmented data, we can actually have copies of the rows crossing training and validation. So if we compute cross-validation score for our model, we will be effectively computing the capability of the model to do in-sample predictions rather than out-of-sample predictions. So what could be the solution? We shouldn't do that. Partition first, then augment. So there can actually be multiple solutions to this issue. So you either copy first and then apply group partitioning, like the third version of Andrew Ng's paper. So like you do make your copies first and partition them as groups. Or you should partition first and then augment only the training part. So I would actually advise to augment only the training subset of your data and leave the validation as it is. So you should partition first, then augment, not copy first, then random partition second. Or if you make copies, make sure to use group partitioning so you don't have copies split between different folds of your data. So another question, another mistake I've seen people do. So what if we apply random partitioning, but our data is actually a time series? For things like Kaggle competitions, it's not always obvious whether data is time series or not, but if we know that our data is time series, would it still be okay to actually apply something like k-fold cross-validation? Turns out if we apply random partitioning to a time series data set, we can have a situation like this. So imagine it's a stock price for a company like Apple Incorporated, and if we compute validation scores for a model like this in a partitioning setup like this, we will be effectively evaluating how well can the model predict the past given the future and the past. So it's useless for the problem we're trying to solve, because we would like to solve the problem of seeing historical chronological data and predict a chunk of future data. So we have to actually repeat the same setup in our validation framework. So if we have to deal with looking at historical data and predicting future data, we have to repeat the same process in our validation and introduce something called out-of-time validation. So I've seen different names used for this approach. And so somebody call it, some people call it backtesting, some people call it forward steps in time, some people call it time series k-fold validation. So I prefer using like either the term out-of-time validation or backtesting. So we train our model on a chunk of the past and predict a bit of the future. Then we extend our past a bit and predict some even recent future. Then we extend our past some more and predict some more future. So we, just as we did with the cold start problem and out of group validation, we have to repeat the same challenge during our validation setup that our model will have once we deploy it into production. So since in production our model will have to always deals with the future, we have to present the same challenge to our model during the validation stage. So remember, validation here is always our friend. We should make sure that the validation setup we have for our machine learning experiment actually represents the problem we're trying to solve once we deploy it into production. So what can happen once we've done feature engineering properly, once we've done partitioning properly, once our validation setup looks good? Turns out there's actually a few mistakes we can make in training and tuning as well. What can sometimes happen? I will admit that the results of that will probably not be as significant as the mistakes made during data collection or partitioning, but a slight mistake I've seen people do as well, make as well, is overusing the same validation split for multiple algorithms. So for example, in a typical real-world modeling scenario, the challenges you face are what model works best for this data set? What set of features works best for this model? What hyperparameters work best for this model? So we have to do feature selection, we have to do model selection, we have to do hyperparameter tuning. And if we overuse the same training and validation split, we can actually inadvertently overtune our model a bit to the exact rows in the validation fold. What's useful, like the kind of thinking that is useful to prevent this kind of issue is we should treat model selection and feature selection and hyperparameter tuning as kind of separate machine learning models that have to be validated separately. So we have to, it's better to use one validation split for hyperparameter tuning, so like, for example, internal cross-validation for hyperparameter tuning and external cross-validation for model selection, and actually use different training and validation splits for multiple algorithms we would like to learn and evaluate. So we, like, in this mode of thinking, feature selection is a separate machine learning algorithm. We have to validate it separately. Model selection is a separate algorithm, and we need to validate it separately. And same applies to hyperparameter tuning. This mistake relates to model ensembling. So it's pretty common in competitive machine learning, but sometimes people do this outside competitive machine learning as well. So we know that there's an interesting technique that can boost the accuracy of our model. So instead of building a single model to predict something, we actually build a committee of models. And a simpler way of ensembling would be to build a committee of models and average their votes. A slightly more complex version of ensembling is doing model stacking. So, for example, we train, we build a committee of a gradient boosting machine, a neural network, and an elastic net, and we stack them with another, like with a decision tree, or stack them with another neural network. So we have a committee of models and the chairman of the committee who listens to the votes of the committee and passes the final judgment. And the way it's described in the literature is that we should use the predictions of the first level models as features for the second level models. So we make predictions from our neural network, we make predictions from our gradient boosting machine, we make predictions from our elastic net, and we actually have this matrix with 3 columns, and we use them as features for the second level model. This way of doing stacking is completely wrong, because we will actually be making those predictions in samples. So if we train on the entire data set, then predict the entire data set again, we will be actually making in-sample predictions, and they will strongly give away the target for the second level model. So they will leak the target because they are in-sample predictions. We've already seen them during training the models on the first level, so it will carry strong signal for the target and will not generalize properly. So the way to do stacking better would be to actually always make out of fold predictions for first level models. So we have to make sure that the first level models still make predictions on the pieces of data they haven't seen. And the way we do this, we allocate our typical k-fold split, and we train our first level models on 4 chunks of data and predict the 5th, then repeat this process 5 times, or maybe like 10 times or 20 times if we had 20-fold. And we always only have a little, chunk of predictions. We don't predict the entire data set all the time, but we only make a small chunk of out-of-fold predictions. So we predict 1/5 of the data, then again predict 1/5 of the data, then again predict 1/5 of the data, and we collect those predictions and stack them together. That's why this way is sometimes called stacked predictions, because we like stacked small chunks of predictions together, made out of fold. So this process gets increasingly more complicated once we have more than 2 levels of stacking, but yeah, this is the general way you should be approaching this. So if you use predictions of the models as features, those predictions should better come from out-of-sample data rather than in-sample data, because otherwise you will be leaking the target. So entirely different section of target leakage, but still a very interesting one, is leakage in competitive machine learning. So I will admit that leakage that happens in competitive machine learning, like Kaggle competitions, does not necessarily happen in real-life scenarios when we build models to solve particular business cases. But the reason I included competitive machine learning here is it's an excellent source of how tricky target leakage can sometimes be, and how exotic it can be, and how tremendously it can be exploited to gain better predictive scores for the model. So one example of this, it's a very interesting case study of target leakage that is very subtle and very tricky to exploit, but gives a nice boost to predictive accuracy. So this example is from Expedia hotel accommodation competition that happened a couple of years ago. The challenge there was mostly about given the search terms of a user who looked for hotels and having the information of the exact hotel they booked, so we had to, the data set dealt with hotel recommendations, bottom line. And to anonymize this data, the competition organizers removed like user IDs, removed user locations, so we don't know where the user lived and where the exact hotel that they booked was located, but we only have the distance feature. So we only had the distance between the user's city and the hotel they eventually booked. So we did not have the location of the user, we did not have the location of the hotel, we only had the distance. And turns out if you have a lot of data like this, you can actually map all different distances on a globe and kind of triangulate the data to pinpoint the exact user locations and hotel locations. So just the mere fact that you remove the location or the user ID does not mean that 1,000 Kagglers cannot reconstruct your user locations or your hotel locations. And like by reverse engineering this distance feature and like trying to triangulate and pinpoint the exact locations on the globe for users and hotels, once we establish the exact location of the user or the hotel, this becomes a highly predictive feature that can be used to boost our predictive accuracy on the leaderboard. So a very subtle example of target leakage, but it can be very cleverly exploited. Another example, it was a competition I participated in recently. Just the fact that you rename column names does not mean that you anonymize your data set. So what the competition organizers did there, they actually had a sequence of transactions, like a sequence of transactions volumes for a bank customer. So each row represented a bank customer, and each column represented some kind of overall amount of transactions over a certain period of time. So like you can think of it as transactions for January, transactions for February, March, April, and so on. This would be otherwise a pretty challenging problem because they not only renamed the features, but for some reason they shuffled the columns in a time series. I don't know why they did that. Like that's effectively removing all the signal in your data, but turns out what actually happened in this data set is that it included rows for the same customers. So for example, the purpose, like the way Kagglers reverse engineered it was given the volumes of transactions over a certain period of time, you have to predict the next volume of transactions. So like given spring and summer, you have to predict fall, or given summer and the fall, predict winter. I'm simplifying this greatly. The actual problem looked not quite like that, but I'm simplifying this for a matter of a thought experiment. And by including multiple rows from the same customers that span different time ranges, we can actually have a row for a customer that has January, February, March, April, and May, and we can have another row for the same customer that has March, April, May, June, July. So if we want to look at the data for the winter and spring and predict summer, we do not have to build the predictive model. We just have to find the row for the same customer and look at the exact answer for like what transaction volume they had in July or June. So because you anonymize the column or the columns, or you shuffle the columns, does not mean that a data scientist cannot apply unsupervised techniques to find out that the multiple rows can relate to the same user, the same customer, and like reconstruct the alignment of these rows such that you can easily grab the target, like the answer to your problem from another row in the data set. So still a pretty exotic and interesting case of target leakage. Another example of target leakage is your target leakage must not necessarily be in the data itself. So an interesting example of this was a truly native competition a couple of years ago. So the overall problem was given a file with HTML content of a web page, you had to predict whether it's sponsored content or not. So it's a binary target. You are given a bunch of files with HTML content in them, and you have to look at the HTML content and predict whether it's a paid content or not, paid piece of content or not. Turns out, so if you think about this competition as a competition organizer, so how do you create a competition data set if you want to launch a competition like this? So you go into your database, you export some rows that are not sponsored, and you export some files that are not sponsored, and you export some files that are sponsored, and you zip them together and ship it as a competition data set. So what actually happened here is the creation date of the file completely gave away the target. So positive row files were created with one timestamp, and negative row targets were created with a different timestamp. So you don't even have to look into the HTML code, you just have to look at the file creation date. And like with a simple if statement, you can classify whether it's sponsored content or not. So sometimes target leakage can come not in the data itself, but in the metadata. If you're in a competitive environment where everything that matters is just getting a better leaderboard rank and not necessarily solving the end business goal. And another peculiar example is especially when we have pairwise data. So if you remember last year, my presentation at AI Ukraine was about paraphrase detection in NLP, and it included some examples from the Quora competition. So it had an interesting example of leakage here. So we're given 2 question titles, and we have to predict whether those 2 questions are asking about the same thing, effectively. So whether question 1 is a paraphrase of question 2. So if we think about it, if we were a data scientist at Quora, and we have 1 million of questions in our data set, what are the odds that if we take a random 2 questions, what are the odds that they will be duplicates? It will be a very, very, very small probability. But actually, in the competition data set, duplicates were 1/3 of the data set. So we have a heavily oversampled minority class. And this opens up possibilities for reverse engineering the process of how the trained data set was constructed. So the mere presence of a question in a pair, so if our question is involved in duplicates a lot, that means that the presence of this question hints towards a positive answer. So the way to exploit this leak would be to build a co-occurrence matrix of questions, like which question occurs with which question. And SVDing that matrix would give us a very strong predictive feature that shifts the probabilities our model predicts towards a better answer. Of course, it's completely unusable in the real world scenario, but if you care about getting better accuracy scores on your predictions for the competitive environment, this is a really clever way to exploit a very subtle leakage introduced by artificially oversampling the minority class. So these are the examples of various mistakes you can make during different stages of your data science project. So an obvious next question would be, how do we prevent how do we prevent target leakage when we have a machine learning experiment? Because this, as you have already seen, this problem is quite subtle, and there is no silver bullet solution that can work for any kind of mistake you can make in any of the data science project stages, but there are a few pieces of advice I can actually give here. So an obvious first advice would be to, as we've seen from the issues with feature engineering or partitioning, you should do your best to split the test set away immediately and not look at it in any way until you've come up with the actual model you would like to predict. You cross-validated this model, you feature engineered the features for this model, you tuned the hyperparameters, you computed your out-of-sample prediction scores, and you are ready to evaluate the predictive accuracy of this model on your holdout set. Only then will you look into the test set. So my first piece of advice would be to split the test set away immediately and do not touch it until you've come up with a final deployment-ready model that you're ready to test. So for issues in data collection and data preparation, you need to make sure you have a data dictionary. So what makes target leakage an even more difficult problem is that for large-scale data science projects, there are different teams and different parties involved in exporting the data, preparing snapshots of the data, and feature engineering. So you can have a team of data engineers who perform the initial data export, and only later you have a completely different team of data scientists trying to build a model that predicts the target given those snapshots prepared earlier by data engineers. So different groups of people involved in a data science project might not necessarily know the business implications of each feature, and might not necessarily possess enough domain knowledge to know what kind of features you should export and what kind of features you should ignore. So if you imagine a real dirty data set where you can have thousands of columns, it's easy to overlook a copy of the target encoded in some cryptically named feature somewhere in the middle of that data set. So that's why making sure you have a data dictionary and you actually understand the meaning of every feature in the data set that you use for modeling is a good step to prevent target leakage introduced during data collection stages. And for the same kind of problems, I would advise to answer the following question. So if we come up with the actual set of features we're using for our final model, and we're ready to deploy this model into production, we should make sure to answer this question. Like, for each feature in my final feature set, will I have the value for these features in production? So this will allow us to avoid the issue like using late payment reminders as a feature for a credit risk scoring model, or how many surgeries our hospital has performed, like when we only try to detect whether the patient has this disease or not. So we should try to answer this question, like for each feature that we use, will the values for this feature be available to us at prediction time, and what kind of values can it have? So can it have the same values as we had in our training set? So yeah, with feature engineering or data preprocessing, we should figure out the parameters on the training subset and only use them, freeze them, and transform the test set afterwards, not infer anything from the test set. So yeah, with group partitioning, with time series partitioning, we have to do our best to make sure that our validation framework actually represents the challenges our model will face in production. So if we're dealing with cold start, and if we're dealing with out-of-group predictions, we have to use group partitioning, group validation. If we're dealing with a time series forecasting problem, we have to partition our data in a time-aware fashion and always train on the past and predict on the future, not do random partitioning or anything like that. Also a very useful technique that can even be automated to some extent. Nowadays we have model agnostic algorithms to evaluate feature importance for any kind of model, or explain the predictions for any kind of model. So you can think like Lime or SHAP or anything else, or even something as simple as XGBoost's feature importance plots. Once we're ready to deploy the model, we should look at the prediction explanations and the feature impact of each feature and try to answer the question, like from the domain point of view, does it make sense that this feature has such high impact, or does it make sense that this prediction can be explained by this feature? So you can actually apply it. You don't have to necessarily use something primitive as linear regression or a decision tree to have these kind of insights. There are algorithms that can work with arbitrary black box prediction models and still have some kind of notion of how important each of the features is. So those algorithms vary in their usefulness and accuracy, but still something that can give you a nice tool for domain validation. Yeah, so that would be all. I'll be happy to answer any questions you have, and feel free to catch me anytime during conferences if you'd like to follow up more.
Yuriy, thank you for your talks. Andy, we have a question. No. Yes?
Hi, thank you for your talk. Can you please return to the slide where you described a specific leakage case for the training stage?
Yep.
Yeah, and as far as I understood, you mentioned that like for different models, you really need to create like different splits, right? Like to measure the quality. But I have to argue that sometimes the mean value of a metric across the different faults is not really a good indicator of performance, because sometimes the metric itself, or just the data size is very small. This metric can be like very noisy, and you're really required to not to compare the means, but rather to compare the distributions over the different faults. For example, like very common technique is to create not 5 faults, but also 50 faults, and then use some kind of paired test to say if the model is better than another. And in this case, you're required to test on the same faults.
Yeah, that would be a valid point. So the main point I was trying to make here is that we should make sure to not overuse the same validation test for multiple things we need to validate, or especially like using the same folds for multiple level stacking. So we have to like change seeds or change splits. Yeah, so I do agree that the impact of this can be quite subtle, but like many, it can surface in competitive environments when you start fighting for 4th or 5th decimal points in your accuracy scores. And actually, you made a good point that sometimes if you want a more robust assessment of the predictive quality of your model, you can sometimes evaluated on multiple k-fold splits at the same time and use not only the mean, so I'm not necessarily advocating for using the mean, but yeah, looking at the distributions is good. It's especially useful for validating time series models. So let me try to rewind. My filter does not work for some reason. Anyway, so if you have backtesting in your time series model, you can actually gain a lot of insights from backtesting validation scores in your time series model. You can capture some things like, does your model treat, deal well with seasonality or deal well with an exponential trend? So I would agree that distribution is very useful. Or actually not only using the same cross validation, but evaluating the model on multiple cross validation setups and averaging the predictions and looking at the distribution.
Thank you.
Yeah, that was a good point.
I agree conceptually with the point that you made that it's a good idea to split your training and validation sets before you do anything else. But I was just curious about the point that you made that if you don't do that and you standardize your whole data set with like standard mean and standard deviation first, then it could cause some leakage and cause you to have better performance on the validation set than you get in production, because I guess I was just having a hard time imagining an example of how that would really materially help you.
There's actually a code example I made for that. So I picked a model that's very sensitive to feature scaling, which was k-nearest neighbors with a low number of neighbors. And there are some effects you can see in this code example. So this primarily occurs. So it's easy to overlook it. In many cases, it might not have any effect, any visible effect at all, but it can happen in presence of extreme outliers in a data set when the model is sensitive to outliers.
Okay.
Yeah, so you kind of give hints to the training set, like, hey, I will have an outlier for you in the test set, so be aware of that and adjust your mean and standard deviation for scaling. It can very often it might not happen, especially if we use tree-based models that are more robust to outliers than linear or KNN, but yeah, small effects can be seen.
That's all maybe. Thank you all.
Thank you.